Hello guys, I'm a teacher Olimboka Nsajuga Masame. Welcome to Olimboka Physics. The question below states that a hiker stands on a solitary mountain peak near sunset and observes a rainbow caused by water droplets in the air at a distance of 80.00 km along her line of sight to the most intense light from the rainbow. The valley is 2.00 km below the mountain peak and entirely flat. What fraction of the complete circular arc of the rainbow is visible to the hiker? Okay, let us consider the diagram below. Let's say elaborate the scenario. We assume the sun is at left side, and this is the sun rays that strikes the water droplet, and the emergence ray is red. We assumed this is a rainbow that formed due to primer rainbow formation, 1 reflections and 2 refraction. Okay. This is a deviation angle in anti-clockwise directions. Okay, and this angle of deviation for red is commonly known, and it is for primary rainbow, and it is 42.2 degrees. Okay, this is the mountain top where the observer stands, and this is next mountain, opposite mountains, where his or her line of sight touch the top of the mountain, and below it is a valley, is 2 kilometers to the valley. As you can see, this valley that is entirely flat with rivers in the middle, and the most intense light from the rainbow, as you can see, this red, and this as a next color. Okay, the condition for this intense color is as explained here. The changes of angles of deviation with respect to incidence angles of sunlight must be corresponding to minimum deviation positions. Most intense color have about the same deviations at the minimum value, and thus image almost parallel. The most intense color, as you can see here, has the same deviations at the minimum values as this angle of deviation for each respective color changes with respect to their incidence angle. Then the changes is corresponding to a minimum angle of deviations, as you can see here. This is the point where the emergency angle is equal to incidency angle. Okay, and for these conditions, the emergency rays are almost parallel to each other. As you can see, these emergency rays are parallel, and they're also parallel to the incidence rays. And at these conditions, which is where we can get the color to be distinct and the intense, bright to an observer eyes. Okay, for this condition, it says that for minimum values of these deviations, the change in deviations with respect to the incidence angle is equal to 0. Okay, for primary rainbow, m is equal to 1, and for secondary rainbow, m is equal to 2. From our questions of total angle of deviations from above there, then when we differentiate, we have result for primary, and we have this result for secondary, and this marks as the equations 1. And but the n is the effective index of water, and the other is the effective index of air. Then from Snell laws, expression will become, as you can see here, and we put a green stars. Then this we mark as equation 2. And now let us differentiate these expressions. After differentiating this expression, we get this expression which is equal to equation 3. And for a primary rainbow, we substitute dr over di, and for the second rainbow, we substitute this dr and di, as you can see here. And then we take square to both sides. Then we will have these expressions. We needed to find to omit this r. Then we use the trig identity to remove this r from this causes square r. By using trig identity, we will result to this expressions and these expressions. Also, we are supposed to remove this sine square r. Our aim is to have this incidence. We will remove this by considering the second equations here. We mark with green. Then we substitute this value of n sine r. We substitute sine I, so that we will have sine I square to n squares, and this one has been omitted by or replaced by sine I. After that, we do some simple mathematical algebra here, and we will have a result as you can see here for primary and this is for the secondary. And for incidency of red, we know that the diffractive index for a red color is 1.331. Then we will do for incidence for primary and incidence for secondary, and we will have that as you can see this one and as this one. And for refracted rays, then we will go direct to the second equations, and then we will be able to find the refracted for red, and for primary, red for refracted angle for secondary. As you can see here, this is 40 and 40/80. Then from the early questions, this is for total displacement, for total angle for observations, then you will substitute, because there is I and there is R for corresponding primary. This face is for primary, and then we will get to 137.80 degrees for clockwise direction. Remember, this is clockwise directions, but for anti-clockwise directions, for clockwise directions, this one to here. Okay, this is clockwise directions. For anti-clockwise directions, this one from here to here, we must take it and subtract it from 180 degrees. Then we'll have 42.2 approximately for primary rainbow. Do the same way for the secondary rainbow. From our questions, now let us consider our questions. Then we will consider triangle NHM, we consider triangle NHM, and triangle NHO. Okay, after considering these two triangles, then we will have tan theta for NM and NH, which is equal to 14.034 degrees, and NHO is equal to 42.2 degrees. That proves angle of deviation for red in clockwise directions. As you can see, this is 42.2 degrees for red. Okay, after doing that, in order to get the eyes of the angle that is subtended by the observer eyes to the part of bow, we must add this two angle, and we get 56.2 degrees. As you can see here, 56.2 degrees at the angle beta. Okay, for then for 180 degrees bow, the second eyes also view at 56.2 degrees. Also, second eyes view at the same angle, subtended angle. Then we must subtended angle must be multiplied by 2. Then from fraction of circular arc, then we apply the arc formula, and we cross this 180 degrees, cross this pi, and this radius of the bow, it is constant, it is cancelled out. Then we remain with this fraction, this total, which is 180 with angle beta times 100%. Then from there we will have a percent fraction of circular arc that the observer eye will subtend is 62.4 degrees without approximation, or 62.2 degrees with approximation. Please like, share, comment. Don't forget to subscribe this YouTube channel for more video like this one. Okay, thank you.